In chapter 4, we will be looking at stereochemistry. So in this lecture, we will cover the definition of stereochemistry, and we will do some comparisons of molecules in 3 dimensions. For this lecture and for this chapter, you will definitely need your model set. So my suggestion at this point is to pause the video and go get your model set and get ready to build some molecules which we will be discussing in this lecture. Okay, so far the stereochemistry that we have looked at, remember stereo here means orientation in 3D space. The stereochemistry of molecules that we have looked at so far are conformational molecules or conformational isomers, sometimes referred to as rotamers. And here they differ based on rotation about a single carbon-carbon bond. So as you can see here, this has a seal at the bottom and a seal at the top, and here's at the top and right beside it. So that's a gauche conformer. There are 2 different conformers of the same molecule. The other stereochemistry that we looked at is the cis and trans, in that we have a rigid double bond or rigid aspect of the molecule, and we have different groups that are across that rigid structure. So that's a cis or a trans, depending on if they are on the same side, it would be cis, and of course if they are on different sides, it would be trans. Okay, but let us look now at a different type of stereoisomers. So let's look at these 2 molecules carefully, and you may want to build these 2 molecules here. So what I've shown here is a molecule here that has a carbon and has a white, a yellow, a green, and a red. The same molecule here exists because it has a white, a yellow, a green, and a red. So it has the same atomic weight, it has the same number of groups bonded to the carbon. The question now is, are these 2 molecules the same, or are they different molecules? Or different isomers, I should say. Isomers is a better term. So are they the same, or are they different isomers? Looking at it, it's very difficult to determine unless you have a way of determining if they are the same or different. It's like asking you if your right hand is the same as your left hand. That's a tough one because they look pretty much the same. So what we'll do first is we will determine a method to distinguish isomers if they are the same or are they different. So let us look at that definition or that criterion. The criterion that we look at here is superimposability. So if these 2 molecules are superimposable on itself, and when I say superimposable, I mean all the atoms overlap. All the atoms overlap. And in that case, they are superimposable. If all the atoms do not overlap, then they are not considered superimposable. So that's the criterion, or one of the criterion, that we'll use to determine if 2 molecules or 2 isomers are the same or different. So what I've done here is to take those 2 isomers and superimpose them on each other, and as you can see, the green overlap, the red overlap, the yellow overlap, and the white overlap. So therefore these 2 molecules are in fact the same because they overlap and they are superimposable. Let us take it a step further. The question now becomes, can you apply the knowledge that you have gained in the dashed wedge method of representing molecules? So here are two molecules using the dash wedge, dash and wedge, and of course in the plane, and the same groups are bonded to that carbon. The question now is, are they the same or are they different? So what you can see here is you'll have to utilize the definitions that we have developed and the representations that we have developed previously to communicate 3D structures and somehow twist them around in your mind or in your brain so that you can come up with a conclusion, an answer. So let us look at this. So for these two molecules are in fact superimposable on each other. So therefore they are the same. So you can expect questions like this on your quiz and of course definitely on your exam, because we as chemists, we feel that this is an important part of the scientific development, which is developing that 3D analysis of your brain and using it to come up with solutions. So again, what we have to do here is to imagine or visualize a molecule in 3D, represent it using the dashed wedge, and compare that to another molecule that's very similar with the same atoms around it and determine if they are superimposable or not. Okay, let us look here at another example. So let's get back to the same aspect here. Now I have two molecules, carbon, a red, a yellow, a green, and a white. Same, a red, a yellow, a green, and a white. So the question now is, the same question is, are these two isomers, stereoisomers, are they the same or are they different? So what you'll have to do here is to visualize, are they superimposable on each other? If they are the same molecule, and if they're not, they are actually different molecules. They are in fact different stereoisomers. So let's see. So what we have here is a very cumbersome looking way of describing it, but as you can see here, the white overlap, the red overlap, but the green and yellow, they do not overlap. I encourage you to build these two molecules and try doing that using your model set. Since they do not overlap or they are not superimposable, they are not the same. They're not the same. They are stereoisomers of each other, different stereoisomers. So we have to give it a different name. So far we've looked at conformational isomers, we've looked at geometric isomers. These are not geometric isomers. They're not conformational isomers. Let's coin a term for this relationship. The term that we'll coin here is enantiomers. So these two molecules here, they are stereoisomers that are not superimposable on itself, so therefore they are enantiomers. That's the name of it, is enantiomers. Let's make another important observation here, and that is, here we are imagining a mirror. So here's a mirror going right down the middle of this. So this molecule here is being reflected on this molecule here. So they are in fact mirror images of each other. Okay, so that's another observation, is if stereoisomers are mirror images of each other, then they are different, and the relationship is they are enantiomers. So these molecules are stereoisomers, and to be specific, they are called enantiomers. So now we're going to try to apply that concept using the dashed wedge, etc. So let's see how we can do that. Before we do that anyhow, let's look again at another aspect here. And that is, this is another observation, is that this molecule here, it does not have a plane of symmetry. In other words, if you put a plane right through, going through the center of that molecule, one half will not reflect on the other half. You cannot find a plane going through that molecule where one half reflects on the other half. So we say that it lacks a plane of symmetry, or it does not have a plane of symmetry. So all these observations now are here to guide us and help us in determining if two stereoisomers are enantiomers or not. Of course, the first is that they are non-superimposable. The second is that they are mirror images of each other. And now the third is that they do not have a plane of symmetry. So again, you're getting all the tools to analyze a molecule to determine if a molecule that's very similar in terms of atomic arrangement and groups that are bonded to a carbon, are they the same or not? Okay, so let us go on here. So this is what I was talking about here, and that is, now let's use the dashed wedge representation. Here is the dash and the wedge. So this group here is in the plane, likewise that group, and of course this is in front and this is in the back. That's a dashed wedge. Of course, as you guys know from biology, this is also called alanine. It's an amino acid because we have the amino and the carboxylic acid, so it's called an amino. It's called an alpha amino acid because the group is bonded to the alpha carbon, the first carbon. But the bottom line is, as you know, that the L amino acid is different from the D amino acid. In the biological system, the body recognizes these two this difference. And as a matter of fact, one is the poisonous one, and the other one is the one that builds into peptides and proteins. So they are very different molecules. The body can recognize that, but on paper, they look very close, look very similar, except in the three-dimensional arrangement of the groups or atoms bonded to the central carbon. So these molecules are known as stereoisomers, and to be specific, they are called enantiomers. Enantiomers, so they're not the same molecule. So you know where this is going is that you'll be given different molecules drawn in the dashed wedge representation, and you need to determine if they are the same or are they different in terms of enantiomers or the same molecule. Let's see here. So here's what I was saying earlier. This is the real biological importance of chiral molecules or enantiomers, and that is, of course, as you know, to bind in the biological system, it has to have perfect binding for biological activity. And one molecule here, that is the enantiomer, has perfect binding, and its enantiomer will not have perfect binding. So this is the one that is active, and this is the one that's not active. You'll see in the book where we have different examples of enantiomers. Ibuprofen is one. It's one in which its mirror image is not the same as the original. So therefore, and one is active, and the other one is even more effective in headaches and so on. Okay, so let's look at another term here, and this is stereogenic molecules. So this is another term that we'll use, stereogenic molecules. is one molecule that has a carbon that has 4 different groups bonded to that carbon. 4 different groups. So this is another observation. A carbon that has 4 different groups bonded to it. Its mirror image will be different from the molecule, and therefore it will be the enantiomer. Okay, so we have another term here, stereogenic molecule, where this carbon here is called the stereogenic carbon. So again, we'll use these terms as we go through the course, stereogenic molecule, and we'll also use another term called enantiomers and plane of symmetry and mirror images. They're all making reference to the stereochemistry of molecules. Let us look at this molecule here. This molecule here, this is the carbon, but notice that this group is the same as that group. So it's non-stereogenic carbon, and this molecule is not stereogenic. So therefore, its mirror image will be the same as the molecule. So its mirror image is not an enantiomer. It's not a stereoisomer. That's different. So look out for that. Again, for this chapter, you will have to do a lot of practice. You'll have to get your model set and really visualize these molecules in 3 dimensions. Okay, here is another aspect. What happens in 3D is that ever so often a chemist comes around and say, well, gee, I have a much easier way of representing molecules in 3D on paper or in 2D. And Fisher came up with another representation. So this is not the dashed wedge. It's called the Fisher projection. And what he envisioned is to hold the molecule like this, so it's pointing towards you. And this bromine, for example, and this hydrogen will be in front, and this methyl group and this chlorine group will be in the back, away from the view. So try to build a molecule like that, having 4 different groups bonded to a carbon, and we'll have these groups pointing towards you, and these groups away from you. Okay, so what we have here is a picture of that. So you can see here the molecule to the left is the dashed wedge, where this red, black, and yellow are in the plane. This is in the back, and this is in the front. So that's your dashed wedge way of looking at the molecule. If you were to look at it in the Fisher, you just have to rotate this slightly over here, where the green comes over here in front, the white comes over here in front, and the red and the yellow would be in the back. So in other words, it's projected so that these groups here are right in front and the vertical are in the back. So once again, the horizontal will be in the front and the vertical will be in the back. So that's the way we're going to represent it, by using a cross. And whatever is horizontal will be in front, and whatever is vertical will be in the back. So here we go. So here is the Fisher projection of an amino acid. Same amino acid, actually, alanine. So now we have a carbon. This is in front, this is in front, this is in the back, and this is in the back. And now we have a carbon. It's in front. This is in front, and back, and back. The question is, are they the same or are they enantiomers? Again, each student will use a different aspect, or may use a different aspect to come to that conclusion. But the bottom line is, we will all have to come to the same conclusion. And which is the answer? Is it the same? Are they the same? Or are they different, which means enantiomers? So you can build your model and try to superimpose it. Of course, on the exam and on the test, you won't have time to do that. But just looking at this molecule here, here's one observation. If we had a mirror right down here, right in the middle, you can see that this hydrogen reflects on that hydrogen, this amino group reflects on that, this carboxylic acid reflects on that, and this which is over here reflects over here. So they are in fact mirror images of each other. So if they are mirror images of each other and they have the same groups bonded to the carbon, they are actually enantiomers. So again, you will have to use different tools to come to a conclusion or to answer the question if these two molecules are the same or are they different. Okay, let's look at this. So now it's becoming a little more complex because now we're looking at the Fisher projection of an amino acid and the dashed wedge representation of an amino acid. The question now is, same question, are they the same or are they different? As a matter of fact, on the quiz that you'll see on Thursday, we have a bunch of questions like this, and you just have to do the analysis. And I especially gave you enough time to figure it out because on the test, you'll have a lot more to figure out in a lot less time. So I want you guys to develop that aspect of your thinking in terms of 3D analysis. So this is the question, are they the same or are they different? So whatever means you use to make that determination, we should get the same answer. Let's see what's on the next slide. So here you can see these two molecules are the same. Okay, so go ahead and build them and convince yourself that they are the same. On the difference here is this is the Fisher projection and this is the dashed wedge projection. Okay, so I think this is the end of this first part of chapter 5. So go ahead and get your model set. You may want to review this over and over again until you figure out how to determine if two molecules that have the same groups bonded to a carbon, are they the same or are they enantiomers? Okay, I'll post the next video soon, which will be on the second part of chapter 5. So continue studying, and remember we have a quiz on Thursday. Okay, bye.